In 1856, American scientist Eunice Foote conducted a simple experiment involving glass tubes and thermometers. She filled the glass tubes with carbon dioxide, water vapor, and then put them in the sun, and found that certain compounds retained heat while others didn't compared to the air. This was the first type of experiment to understand the physical properties of chemistry. She noted in her publication that if an atmosphere like our planet were to increase in CO2, likely the temperature would increase as well. Later on, we'll call these greenhouse gases. Hi, my name is Scott Hamilton Brehm, and I'm an environmental microbiologist. I study the environment through microbes. When I give guest lectures at Montessori schools, I usually tell the kids that microbes are little giants, and rightly so. There's not one place on this planet you don't find microbes. They're everywhere. They're conducting all this chemistry, so they are giant in their little ways. One of the things that they do have to manage, but all life has to manage, is carbon. Revenues in, expenditures coming out. It's like balancing a checkbook. For those of you who don't know what a checkbook is, it's an app. Microbes, whether it's small or medium-sized organisms like us, or even larger, everything has to budget carbon. Carbon in, carbon out. Even the planet, while not alive, has to manage and budget chemistry, and one of them being carbon. Carbon dioxide in the atmosphere. Last 800,000 years, the concentration of carbon dioxide has been fairly stable, give or take an ice age or so. This stability, this predictable climate, predictable seasons, and moderate weather led rise to a species on this planet we call humans. And don't get me wrong, we humans are very clever. We are imaginative, we do lots of interesting things, but we can screw up fantastically so, almost as if we practice. Last 2,000 years, CO2 has been fairly stable. But the last 200 years, during our Industrial Revolution, we learned something. In order to build this society, we had to get energy, and we tapped into an energy source that was in reserve, a sequestered source of carbon called fossil fuels. We burned this to generate energy, to do work, and everything around us has that foundation. But burning that reserve carbon, a carbon that was not part of the world budget, has been adding to our atmosphere. You can see on the graph here, it just skyrocketed. As Eunice Foote noted, this increase in CO2 is resulting in an increase in temperature. What does that mean? Well, the balance is being changed. What we expect to happen and whether that our society has grown into, what we've grown up in, is changing. There'll be more floods, more droughts, sea level rise, erratic, stronger weather patterns. Doesn't sound too bad, but it's a constant, chronic level of grinding. We, as a species, will be faced against this pounding that will cost us in money because we'll be repairing all the time. It will cost us in lives, in land. This is not sustainable. No society can endure this for any length of time. So what do? Well, obviously one thing is we're going to have to reduce our emissions. We're going to have to make our machines better. We'll never stop using fossil fuels, but we'll definitely limit it. We can embrace green energy, fusion. There's lots of things we can do, and we will. We must. But that doesn't address the carbon dioxide that's in the atmosphere right now. Atmospheric CO2 is still there, and it's still rising, still causing problems. So we were starting to build machines, literally big machines, fans to filter air and pull the CO2 out and then sequester it. It's a good idea, but there's some problems. The law of thermodynamics, it's basically the universe's way of saying there's no free lunches. It stands to reason if something's very concentrated, like on the left-hand side of this graph, you don't have to spend a lot of energy capturing it or putting it away or doing anything. It's already concentrated, easy. But a dilute gas like CO2 in our atmosphere, that's on the right-hand side. It's not a matter of pushing a rock up a slow, steady climb. You're pushing it up a cliff. What's inside that red box is the pain point. It's cost a lot of energy to capture that dilute gas and sequester to make a difference in climate change. Everything we do, every machine made, every machine run, every car driven is using fossil fuels, and we are adding more CO2 to our atmosphere. Yes, we will be using green energy in the future, and maybe some new technologies coming down the pike, but we don't have any of that right now. We need to make a difference now. So this is a law. This is a natural part of the universe. We can't get around it. We can't work around it. So what do? What's next? Well, if we go back to the Keeling curve, go back to the increasing carbon. At a distance, when you look at the bigger graph, it just looks like a line. But when you zoom in, that's not as a straight line. It's up and down, a zigzag. Even closer, the crests and the valleys of that. That's CO2 going up and CO2 going down. How much? It's parts per million, 5, 7 parts per million. Well, okay, let's translate it. Gigatons. It's gigatons of carbon dioxide being moved around. I just got done telling you that it takes a huge amount of energy to capture CO2, and yet someone on this planet is already doing it. It's doing it every year. Every summer it goes down, every winter it goes up. What's a gigaton? Well, think of 10,000 aircraft carriers. We don't even have 10,000 aircraft carriers. Okay, think of a block that is the width and length of Manhattan, 45 feet tall. That's a gigaton. It is a planetary scale. This is a planetary problem, and something on this planet is already doing it. I wonder what it is. It's an old technology. We call it photosynthesis. Developed by bacteria billions of years ago, picked up by plants. They pay that enormous bill of energy with tapping into sunlight. They use sunlight energy, capture the CO2, they build up their bodies. That biomass that grows, you see plants, and they do this usually in the summer. And then in the winter, they drop their leaves or things fall and rot and all that, and then the CO2 is re-emitted. This is normal, it's natural, happens all the time. What if we could take a compounded cut of that biomass, keep it from re-emitting? It's gigatons. This is enough to fight climate change. This is enough to curve the Keeling curve. But we would have to tap into that biomass. We would have to do something with that biomass. And usually what we refer to biomass as recalcitrant. Basically hard to work with. Anything you do with it, you actually burn it, it re-emits the CO2. Even if you build something out of it, eventually it will rot and that CO2 returns. So this is difficult. You have to grab hold of that biomass and do something with it. Luckily, we have a ways of doing this. Invented and developed here at SIU by Dr. Ken Anderson is a process called oxidative hydrothermal dissolution. Big word, OHD. It is a way to take biomass and dissolve it into water. Here's the schematic. Memorize the schematic. There'll be a quiz at the end of the talk. It's actually very simple. Heat, water, oxygen, pressure, and we can liquefy any type of biomass into water. It looks like this. This is like a dark tea, if you will. Hardwood, softwood, leaf litter, manure, sewage, anything, cardboard, paper, anything that's carbon-based, we can dissolve into water. This is key because in a water state, we can manipulate it, we can transport it, it's not a compressed gas, it's something much easier, but more importantly, it's now available to every microbe on this planet. Before, recalcitrant biomass is only open to certain microbes, specialists. But in a dissolved liquid state, every microbe can participate. So we have this liquid carbon. We need to fight climate change. We need to sequester it. We need to remove it. Where did we get the fossil fuels in the first place? Underground. We mined it. Let's put it back. There are billions of abandoned and empty oil wells. We could just send the carbon back down there. And this invokes and recruits a second largest contingent of organisms on the planet, the subsurface biome. You may not think about it, but these organisms have been down there for billions of years. They're very ancient. We call them extremophiles. Extreme, not of normal. Philes, to love. Basically, they love extreme environments. Don't tell them that. They probably think we're extreme, actually. So luckily, my lab focuses on culturing subsurface microbes, and we just basically built a microcosm to emulate the subsurface, infused it with microbes from the subsurface, pumped it full of OHD, and just waited and watched what happened. The microbes loved it. They just chow down on OHD, on the carbon. They're going to make more of themselves. They actually reorganize themselves in a trophic level so that they maximize how much they can eat. And this is what we want them to do, because then they'll fix this carbon into the subsurface. This is a laboratory experiment. We're going to expand to field studies. We've already had a third-party evaluator do a techno-economic evaluation. And basically, if we were to make a 1 million-ton facility to sequester carbon, for every 2 tons that we would sequester, 1 ton will pay for the overall operation of the company, of the manufacturing. Remember, everything emits CO2, right? But the other ton would be carbon negative, a carbon negative activity. This is before optimization, before any type of assistance using green energy or anything like that. It is already a carbon negative activity we can do right now. For every pound of biomass, think of a corn cob without the kernels on it, is worth about 1 million liters of air that could be filtered. Just think of how many corn cobs we can go through. The price tag, too, of this is very cheap. It's under $100 to be able to do this. We can do this now, no subsidies, no depending upon a technology that hasn't arrived yet or any type of magical process. This is a conduit that we need, because we currently don't really have it, is to have the CO2 being brought from the atmosphere into the subsurface using plants, embracing the indirect air capture process of the plants, and using the technology of OHD to liquefy it and sequester it deep underground. We can do this cheap, easily, scalable, and like I said, right now. These organisms have been here for billions of years. They've earned the right to be here. We should do the same. Thank you.
Good job.